is a matrix, and it is not like diagonal and one's above the axis. First, we're going to start with the finding all eigenvectors. This is tedious, and everybody probably use some sort of technology to do that. I did that myself. But if you do this 5 by 5 minus ti, that do all the tedious calculation, well, at least I use this t squared, so you see easily the common factor t squared kicks out after you do that, and we have this thing. All right. So what are the eigenvalues? T equals 0 and t equals -4, right? So I go to this matrix, m minus lambda I, plug in c equals 0, and use calculator or Mathematica to do the echelon form to get the eigenvectors. Turns out there's only one eigenvector for that. So that was this v1 with eigenvalue 0 was this, 2, -3, 1, 1, 1. And I did -4, and again, I only got one eigenvector. So this is dimension 5 space, and we only got 2 eigenvectors, and that's it. Right? So what is the next hope? Is that you do that pulling it back for each of the eigenvector. And you saw that from problem number 1, that big chunk is indecomposable as you pull back. So I go here. This is a v1 with eigenvalue 0. So decided to pulling it back. This is from problem 1, right? Going for the w. Here's an eigenvector. That v1 goes to 0 under that map. v2, this is a matrix that I had used the echelon form to calculate this vector. So I solved it, v2. So v2 under that operator go to v1. And I did one more time. I'm looking for v3. And what is going to v2? And I solved it. It says not solvable. So I stopped there. I can't do that anymore. So I have this v1 and v2 is under the chain condition of this map t minus lambda I here, matrix m minus 0 i. Does that make sense? So we got this w piece here. So v1 and, so I'm writing in here, v1 and v2 is under that chain condition, and this is indecomposable. Remember, that's indecomposable. That's from problem number 1. We have another eigenvector. So we're pulling it back. Here's an eigenvector that's supposed to, if w goes through 0 here, so solve for w2, use a calculator, turns out this is the vector. So that's w2. I'm putting it in here and solving for w3 again. It was solvable. It got a little bit ugly like this. And I tried again one more time, w3, and looking for w4, it says it's not solvable. So I have these 3 vectors, a span, and I have 2 vectors and 3 vectors, and you put it into, and you know easily that u and w, they are indecomposable from the problem number 1. Anything that's out of that construction is indecomposable. And I have 5 vectors in here that generates that, and you can put those into an echelon form, see if they're linearly independent. That's easy, right? Since you're using echelon form. And it turns out they're all linearly independent. And that's, I think, what I'm doing in here. I'm sufficient. There are v1, v2, w1, w3. Put it into this all matrix. That's v1 and v2 and w1 and w2 and w3. Echelon form says diagonal. What this means, these are all linearly independent. All right? Does that make sense? Echelon form. This linear dependence of this echelon form is the same as linear dependence of this echelon form, right? There's this very, very interesting theorem. So these are all linearly independent. 1, 0, 0, 0, 0, 1, 0, 0, 0. The column vectors are the linearly independent. That linearly independent is exactly the same in here. That's the magic that echelon form is doing. Therefore, this u and w, not only it's a direct sum, its dimension is 5. It must be exactly the R5. Right? So u is indecomposable, w is indecomposable. They together make the complete thing. It happened to be the decomposition. Decomposition into 2 vector spaces that are indecomposable and invariant. And part D is asking you to compute the matrix under this basis. v1, v2, w1 and w2 and w3. So I'm doing it carefully here. v1 has this chain condition, and you rewrite it what it means for mv1. So mv1 is 0 times v1. That was an eigenvector of eigenvalue 0. So 0, 0. What happened to mv2? You solve for mv2. then is V1 is there and V2 is over here. 0 V times V2. So what happened to V2? It goes to 0 V1 and 1 V1 and 0 V2. Those coefficients become column vectors, right? That's how the matrix of coordinate system works. So here is there and is there. So that's the matrix that does not involve any W1 and W2 and W3. So in the big matrix, this appeared in the upper left corner with all 0 down there and there. And if you look at W1 and W3 through 3 and you do exactly the same thing, and then it appears like the -4 and 1, -4, little shift it's appeared in here with 1 above the diagonal. We've seen this one before, right? These are the intercomposable. So if you put them all together, all 5 bases, new bases, carefully chosen bases, the matrix looks like this. The one intercomposable of a typical shape that I introduced several classes ago, this one like that. It's going all the way down, changing the eigenvalues. We have ones above the diagonals. From here, you can see that easily intercomposable spaces like that, but it was opposite direction. And next problem, we do exactly the same thing in a number 6, smaller size but over complex. So if you try that, and the determinant, the characteristic polynomial looks like this, and not too bad. It's kind of in a quadratic form, quadratic type, further composed like this. It doesn't factor any further, but it factors over the complex numbers. So if you factor that, it's a 6i and -6i. Then you look for, because we're in a complex, and you look for eigenvectors for 6i and -6i. And repeat exactly the same thing with nasty complex numbers. Then turns out there's only one complex value for each of the complex vectors for each of the complex eigenvalues. So we don't have 4, it's a dimension 4, right? So we don't have 4 eigenvectors, so you have to kind of pulling it back and figure out that business again. And it turns out, if you do repeat that same thing, there's eigenvalue 6i, and there's a pullback, so there's 1 up there. For eigenvalue -6i, it pulls back 1 time, looks like this. So that's the matrix with the complex coefficients. Okay? Those were the homework. Any question? Block. Right. But if you choose the wrong basis, and then it's this side here is going to be ugly, but at least you can kind of separate it. Invariant part makes your block matrix, and carefully choosing in UNW, the basis, by pulling it back, make each of the block matrix into this semi-diagonal form. Okay? This form has a name. I'm hiding it until everything is over. But I'm going to call semi-diagonal form. All right? That's not the standard term. All right.